We're going to take a look now at the next section of our chemical bonding unit. Now, at this point, we should be basically pros at our VSEPR theory and predicting molecular shapes. We know about covalent and ionic bonds, and we know that it all has to do with our valence electrons. We've briefly talked about electronegativity, but I want to go further into looking at electronegativity to figure out why these numbers exist and what they mean for us in terms of our molecular compounds as well as our ionic compounds. Then we'll move on and look at a little bit of polarity to see how polarity is also affected by electronegativity. So electronegativity, we've already talked about this in terms of our periodic table. The farther electrons are away from a nucleus, the weaker attraction to that nucleus. So we've talked about how we have different electron energy levels that surround a nucleus, and the farther away that they get, the less attracted they are to those protons in the nucleus. So we call this electron shielding. The inner electrons of any energy level outside of the valence energy level shield those valence electrons from those positive attractions. This means that these valence electrons are available to be bonded with. Okay, now the greater number of protons, the greater attractive force there is to the electrons. However, in general, the greater number of protons in general means that there are more energy levels holding or shielding, those valence electrons from the protons. However, as you move sort of towards the right-hand side of our periodic table, we see that there's a greater attraction with the protons because we have more protons, but we still have a different amount of shielding. Now, depending on the electronegativity, there's a greater attraction. Okay, now the greater attraction of these electrons means that these elements that have greater attraction means working our way towards the right-hand side of our periodic table, where we know that fluorine has a very high electronegativity. In fact, it has the highest of all of the elements on the periodic table, where it has an electronegativity of 4. But this element has a great number of protons in terms of its row on the periodic table, which means that it has a great pull for electrons. So that is one of the factors that pulls electrons, and this is why it is so electronegative, or part of the reason why it's so electronegative. Now, by using all three of these points, we can assign just a relative value. Now, the important point is that it is a relative value, okay, that describes how well an atom attracts electrons, okay? So, electronegativity is the relative ability of an atom to attract bonding electrons in its valence level. Fluorine has the highest electronegativity of 4, and francium has the lowest of 0.7, which we've seen in a previous lesson. Okay, metals tend to have low electronegativities, and nonmetals tend to have high electronegativities, which is again partly due to the number of protons and the pull of the electrons from that nucleus. So we have a thing called bond polarity. Now, essentially, electronegativity will dictate our bond polarity. And what I mean by that is we've talked about how if we have an electronegative atom that is going to be so much more electronegative that it completely rips off an electron from another neighboring atom, then we call that an ionic bond. It's the taken, not shared analogy. Okay, now if we have an electronegativity of 2 atoms that have similar electronegativities, being that they're both nonmetals, so this would be in our molecular compounds. Okay, so in our molecular compounds, we have similar electronegativities. Now, if we look at this bottom image here, okay, that we have in this slide, we see that there is what we call an electronegativity or a bond continuum. Now, essentially, what we see is on our far right, we have ionic compounds. We look at the electronegativity difference and we say if there is a great electronegativity difference, let's say of greater than 2, we would say that, okay, well, if there's electronegativity difference between our two atoms is greater than 2, then our nonmetal will steal those electrons, or they will take those electrons from our metal atom. Now, if we have unequal sharing of our electrons, meaning that we still have two nonmetals now. Okay, we have a covalent bond, which means that we're dealing with molecular compounds. Okay, but we have unequal sharing. We have one electronegativity that is slightly stronger. It's not so strong that it rips it away like our ionic compounds or our ionic bonds. However, it's strong enough that it pulls or polarizes our bond. Now, if it's nonpolar covalent, we have equal sharing of electrons, or its atoms have the same electronegativities. So if elements have the same electronegativities, or atoms have the same electronegativities, then a nonpolar covalent bond is formed. If the electronegativities of the atoms are different, and they're not so different that it's ionic, we get what we call a polar covalent bond. Okay, so an example of this would be our example with chlorine bonded to a chlorine. Okay, we see that we have two chlorine atoms that are bonded to each other, and there's equal sharing of electrons. Now, this is because when we take a look at their electronegativities on our periodic table, each chlorine atom has an electronegativity of 3.2 and of 3.2, meaning that we have equal sharing of electrons. They're both pulling electrons equally. Where if we look at something like PCl, let's take a look at an example down here of phosphorus and chlorine. Phosphorus has an electronegativity of 2.2, and chlorine has an electronegativity of 3.2. Well, we see here that these electrons are being pulled a lot harder by the chlorine than they are of the phosphorus. The phosphorus is holding on, but it's not holding on very strong. Now this guy is pulling these quite strongly, so we have a polar bond. It's polarized. Now remember that polarized is essentially creating a difference. Okay, so it's not uniform, there's polarity. So we talk about polarity in magnets, we talk about polarity in the Earth, so we have the North Pole and the South Pole. It's the same thing, we have a negative side and a positive side of a bond. So we have these things called dipoles. Now di meaning two poles. Okay, so we have a dipole, and it's all based in our bonds. So we have two poles in the bond. Okay, so it's based on electronegativity, and we show bond polarity pointing from a positive dipole to a negative dipole, and that just means the positive pole or the positive side to the negative side. Now if we go back to our example, and actually let me just jump back here. The one thing I didn't do here, sorry, I'm just going to jump back for 1 second, is I didn't give you an example of an ionic compound. Let's do that really quick before I move on. If we look at sodium and bromine, okay, we get an ionic bond. Because our sodium, I know it's an ionic bond because I have a metal and a nonmetal. However, when I look at my electronegativities, I have 0.9 versus the bromine, which is a 3.0. The difference in these electronegativities is so great that I actually cause a positive and a negative charge on these ions because, or on these atoms forming an ion, because the electron here is stolen by the bromine and it transfers over. Okay, so if we talk about our example here now, PCl, over on this slide, jumping back, sorry. Okay, we see that again our electronegativities are 2.2 and 3.2 for our electronegativities of each of these atoms. Now, if you think of this as the chlorine, because it has a greater value than phosphorus, is pulling harder for those electrons, we would expect more electrons to be existing around this atom, which is kind of what we have drawn down in this bottom right corner. We expect that there's more electrons surrounding the chlorine than there is this hydrogen because, again, our electronegativities are quite different. Okay, they're not so different that chlorine steals the electrons. However, we do see unequal sharing, and that's what we call a polar covalent bond, is that there's unequal sharing of electrons. Now, essentially, if we were to identify these as a dipole, I would say that this side, because it's pulling more electrons, now this gray cloud here is the electrons, this is pulling more electrons, so relatively it has a negative side. It has a negative dipole. Now, because relative to the phosphorus side, that means that this phosphorus side has a slightly positive dipole. Now, again, that is just based on the atom that it's bonded to. If we change the atom that it was bonded to something else, say oxygen and chlorine, you might get a different dipole. These dipoles are all relative. Okay, these are relative to the atoms. Okay, so that's very important to note as well. And essentially, like I said, this bond dipole is just a charge separation that occurs when there's a different electronegativity of two atoms. And we shift our electrons, making one slightly more negative. Again, there's slightly more electrons around this chlorine than there would be around this hydrogen. And the way that we notate this dipole is, again, we show the bond polarity pointing from this positive dipole to the negative dipole. So we'd actually just draw a dipole as almost a vector quantity. Now remember, vector quantities are quantities that have both magnitude and direction. So this actually has direction, and the positive to the negative shows you that essentially there's electrons that are moving towards our negative dipole, or there's a general drift of those electrons to the negative dipole. So we now know, let's just jump back here. We now know that we have dipoles, and we're talking about dipoles in bonds. Okay, so these are called bond dipoles. So we've all just been discussing about the charge separation that will happen in a bond. Now, again, this bond is these electron pairs. Okay, it's an electron pair that is shared between two atoms. And it's just saying that there's more likelihood that there will be electrons towards our more electronegative atom. So when we talk about polarity, there's two senses of the word polarity, and we have bond polarity or bond dipoles. Okay, so we talked about polar covalent versus non-polar covalent. This is a polar covalent bond because we have unequal sharing of electrons, where if we have non-polar covalent bond, we have equal sharing. There's no polarity in that bond. Now we can also talk about polarity in terms of molecules. So we have to talk about dipoles in molecules. So we have a polar molecule, and a polar molecule is a molecule with a negative charge, okay, of electrons that's not distributed evenly among the atoms making up the molecule. Now, polar molecules have partial positive and partial negative charge on opposite sides of the molecule. So essentially, we can look at an entire molecule, the entire entity, and determine if this is a positive or a negative side on the entire molecule itself, or if there's just polarity in a bond. Okay, a nonpolar molecule is a molecule with symmetrical electron distribution throughout the entire molecule. So again, there's no, I'll jot that down, no positive or negative side of our molecule. So that's an important thing to note. We don't have a positive or negative side relative to that molecule. Now, a few things. When we determine polarity of molecules, we have to draw our Lewis formula, we have to draw our VSEPR geometry, okay? And we then assign a dipole to our bonds. Okay, then we draw our bond dipoles, again going from our, let's just draw this in, we go from our positive to our negative bond dipole. Okay, and we essentially then can figure out if there is molecular polarity. So let's take a look. Let's look at ammonia as the example. Let's start by drawing the Lewis formula. We have ammonia, which is NH3. Nitrogen contributes 5 electrons, hydrogen contributes 1 each, being 3, total of 8 electrons. So we get something that looks like this. Our VSEPR geometry, based on the number of bonds and lone pairs, we have a trigonal pyramidal shape. So we'd have something like this. Let's see. Something like this guy here. Okay, so we have a trigonal pyramidal. Now, when we assign our electronegativities, we need to look at our periodic table and check out what the electronegativities of each atom are. Hydrogen is 2.2, and each hydrogen exhibits its own electronegativity, and nitrogen is 3.0. Now, when I compare these numbers, it appears to me that I will have nitrogen that has a greater electronegativity, which means nitrogen is pulling electrons slightly harder than our hydrogen. Now notice there's no stealing of electrons, the electronegativity isn't different enough. However, there's unequal sharing. Now there's unequal sharing between this nitrogen and this hydrogen, this nitrogen and this hydrogen, and this nitrogen and our last hydrogen. So in general, we have a negative dipole, and we have positive. Okay, so we have a general negative and positive dipoles within each of our bonds there. So we draw bond dipoles. Now that's important. Notice how bond dipoles or bond polarity helps us determine molecular polarity. That is very important. So this is how I would assign my bond dipoles. If I was to draw relative dipoles on these bonds, I would say that I have a bond dipole going up towards my nitrogen from this hydrogen. Same with this, and with this hydrogen to my nitrogen. Now, we have to understand how to still determine our overall polarity for this molecule of ammonia. So when we look at adding dipole vectors, and we'll come to these two examples in a minute, we have this thing called head-to-tail addition. Okay, so we have a head-to-tail, which means that this is our tail, this is our head, okay, of our vectors. And what we see is that if we add our head-to-tail addition of our vectors, we get a net or resultant vector. So notice if we have two vectors that add up, we get the net vector being the total magnitude and the direction of our initial vectors. If we have a vector that has the same exact magnitude but the opposite direction, okay, those cancel out. There's no resultant vector. It's like taking 3 steps over to the right and then 3 steps over to the left. You've still ended up in the same exact location. So there's no resultant vector. Now, if we have a vector that's over to the right and then another vector that's up, okay, our resultant vector is using Pythagorean theorem connecting those. It is going up and to the right. So it's instead of right and then up, we basically make a little road map in between and connect the lines, creating a triangle. So if I go back to my example here with my ammonia, I have 3 bond dipoles. One appears to be like this. And if I continue my overall vector addition, okay, so I have one like this, I have one like this, and I should undo, oopsies. Okay, and then I have one that's, I should make these a little bit smaller so I have a little bit of room here. Okay, I have one that looks like this, I have one that looks like this, and I have one that kind of, and I'm going to just draw it down here actually. It's a squiggly line. One that looks like this. So if we were to continue our little triangles here, we would expect this to have a to the right and up vector, and this would have to the left and up vector. Okay, so essentially our left and right vectors cancel out, and then we have this up vector that's now existing in pink and our original up vector. So our net resultant vector looks something like this. Actually, maybe I'll draw an orange. So our net dipole looks like this. Now, we know that generally this is the positive side and this is the negative side. So that tells us that in our ammonia molecule, this general side up towards the nitrogen is our negative side, and this side down here is generally our positive side, and there is a net dipole. That means that this is what we call a polar molecule. Now if we switch over to this slide here, again we have our head to tail addition of our vectors, and we see that we have nonpolar and polar molecules. So if we do the same principle that we did on our previous slide with these two examples, we can check out how polar molecules and nonpolar molecules are different. So let's take a look at carbon dioxide. I have carbon, my two oxygens. Carbon has 4 electrons, each oxygen has 6, meaning that there's a total of 16 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Because carbon's not happy, we move these guys inwards, and we get something that would look like this. And I'm just going to draw the structural formula of this. And we have our 2 electron pairs. We can draw those in here. Kind of a blended between a structural formula and a Lewis formula. So what we see here then is we look at assigning our electronegativities. Now, I might actually space this out a little bit. I'm going to give myself a wee bit more room. And when we look at our electronegativities, I see that oxygen has an electronegativity of 3.4. And carbon has an electronegativity of 2.6. So when I think about these dipoles, I look at my values and I say 3.4 is a bigger number than 2.6, which means 3.4 is pulling electrons harder, which means there'll be more electrons existing here. More electrons existing there means that this is a negative dipole. Okay, this is a positive dipole. Now again, because a dipole is relative to a bond, we're talking about this bond here. However, there's another bond right here. We need to consider this bond. Now again, this is my positive dipole and this is my negative dipole. So when I was to assign vectors, I would say that from my positive to my negative is being pulled this way for my first bond dipole, and for my positive to my negative is being pulled this way for my second dipole. Now, because I have similar or identical electronegativities on either side of this central carbon, and I have a linear molecule, that means that these vectors are pulling equal and opposite. Now, because they're pulling equal and opposite, this is similar to like situation number 2. If I was to draw them head to tail, I would see something like this. I have 2 vectors equal magnitude, meaning that it cancels out. They add to 0. Since they add to 0, this is a nonpolar molecule. Okay, now if we look at a polar molecule, let's take a look at our next example of water. We have oxygen as our central atom and 2 hydrogens surrounding that. Total of 8 electrons, 6 from oxygen, 1 from each hydrogen. And we expect this to exhibit an angular or V-shaped molecular geometry. When we check out our electronegativities, oxygen is still a 3.4, hydrogen is a 2.2. And what we see is that means that this is relative, a negative, compared to this hydrogen, which is a positive. Again, 3.4 is winning that tug-of-war. And because we're talking about bond dipoles, I have to note each bond. 1 bond here and 1 bond here. When I do that, I see that I have a bond dipole from my positive to my negative. Again, my positive to my negative. Now again, if I was to add these 2 vectors up, I would see something like this. All right, and what I would see when I jotted these down, let's do this in this color here, I would see that I have a general right vector and a general up vector. And in this top arrow, this top vector, I would have a general left vector and a general up vector. So what you'll see is that these 2 vectors, this guy here going to the right and this guy here going to the left, they cancel each other out. So all that I have remaining is a general net vector, we'll call it a net vector, of up. I add those 2 up arrows, resulting in a net up vector. So since there was a vector remaining, a net vector, this means that this is a polar molecule. All right, and I could notate that there's the net vector, and I could notate that simply by adding in the vector. And let's just do this in a crazy color so we can see it. And I would just do this like this, that my net vector is like this, meaning that this is my relative negative side and this is my relative positive side of this entity. So I can see how my bond dipoles help me determine molecular polarity. So don't be confused. The only way we have a nonpolar covalent bond is if we have identical electronegativities. And if we don't have identical electronegativities, like this example, I have a bond dipole. By adding the bond dipoles together, I can get a molecular polarity. So this is a polar molecule, this is a nonpolar molecule. However, each molecule, either nonpolar or polar, had polar bonds. They had a bond dipole. Okay, that's important to note. We don't need to do that. So this wraps up our polarity and electronegativity lesson. There will be an assignment down the line looking at electronegativity, polarity, as well as it will have some components of your next lesson, which will be on intermolecular forces. So, good luck!